I want you to start by just visualizing something for a second.
Okay.
Picture the most complex, like highly orchestrated machine you interact with every single day. And if you're not driving right now, just close your eyes for a second and try to map it out in your head.
It's definitely not a machine you can physically put your hands on.
No, exactly.
Yeah.
We are talking about this globally distributed entity, something that processes billions of discrete operations, serves hundreds of millions of people simultaneously all across the planet.
And somehow magically updates its own foundational architecture continuously without ever dropping offline.
Right. Which is wild.
You type a poorly spelled, half-thought-out query into this blank white page, and the exact piece of knowledge you were looking for is retrieved from the collective sum of human history.
In literally a fraction of a second.
Yeah, it is a level of instantaneous retrieval that we have completely normalized. Like, we expect it now.
Oh, totally. We take it for granted.
But the physical infrastructure required to make that actually happen is staggering.
It really is. So today's deep dive is going to take us directly into the engine room of that machine.
I'm so excited for this one.
Me too. We are tracing the architectural evolution of Google's search engine, going from this messy, literal dorm room research project cobbled together in 1997 all the way to a planetary-scale information retrieval system by 2009.
And our roadmap for this journey is such a classic.
It is a foundational piece of computer science history. We've got a keynote presentation given by Jeff Dean.
The legend.
Right. Given at the 2009 WSDM conference, which stands for Web Search and Data Mining, for those keeping track.
Yes.
And the talk is titled Challenges in Building Large-Scale Information Retrieval Systems.
Jeff Dean is widely considered, the architect behind the invisible infrastructure that holds up a massive portion of the modern internet.
Yeah, his impact is just everywhere.
For anyone who spends their life building distributed systems, this presentation is essentially a holy text.
It really is the blueprint.
It lays out the exact physical constraints, the hardware failures, and frankly, the brutal engineering compromises required to organize the world's data at that scale.
So the mission of this deep dive is to demystify that mind-boggling scale for you. We want you to understand not just the code, but the physical and philosophical engineering required here.
Because it's a completely different way of thinking about computers.
Okay, let's unpack this. Starting with the fundamental physics of an information retrieval system. Because an IR system is categorically different from a standard relational database lookup.
Very different.
You aren't just running a quick SQL query to find, like, a customer ID.
No, you are evaluating relevance across an unbounded data set.
Right. It's an active balancing act.
What's fascinating here is how Jeff Dean opens his presentation. He defines the core challenge as this multidimensional balancing act.
Yeah.
He outlines 6 critical parameters that govern an IR system.
Yeah.
And you cannot optimize one of these dimensions without inherently degrading another.
It's just a constant tug of war.
Exactly. So first you have the total number of documents indexed.
How big is the library, basically?
Right. Second is the queries per second, which is the raw volume of user traffic you need to absorb.
How many people are asking the librarian for a book at the exact same time?
Yes, great analogy. Then, the tension becomes immediately obvious when you look at parameter 3.
Which is index freshness, the update rate.
Right, and you pit that against parameter 4, which is query latency.
How fast the user gets their answer.
Exactly. Writing new data to an index to keep it fresh directly competes for the same disk I/O and compute resources that you need to rapidly serve read queries to users.
So if the librarian is busy cataloging new books, they can't be answering questions.
That read-write contention is the fundamental bottleneck of early search architectures.
It makes perfect sense.
Every CPU cycle spent updating the index with newly crawled web pages is a cycle stolen from serving a user's actual search query.
Wow. Okay, and then there's the 5th parameter.
The amount of information kept about each document.
Right, because are you just storing a document idea and a list of words?
Or are you storing heavy metadata alongside it? Things like the PageRank score, anchor text mapping, language classification.
Even font sizes used on the page, right?
Exactly, which feeds directly into parameter 6, the complexity and cost of the scoring algorithm itself.
Because the more metadata you store, the more complex your math can be.
Right, for determining if document A is objectively better than document B for a specific query.
And this is where Dean drops the hammer, the overarching thesis.
The engineering difficulty of building the system is not the sum of those 6 parameters.
It's roughly equal to the product of them.
Exactly.
So it's a massive multiplier effect. If you increase the index size and the query speed, the difficulty doesn't just double.
It grows exponentially.
So if you double the size of the internet you're indexing and simultaneously double the user traffic,
The system doesn't just require twice the engineering effort to maintain. It requires a fundamental rethinking of how data moves through the entire cluster.
because the complexity has quadrupled.
Right. All these dimensions are inextricably linked.
Give me an example of how that plays out.
So, if the search quality team decides to increase the complexity of the scoring algorithm to provide better results,
The query latency naturally goes up.
yes, because the CPUs are doing more math per document.
That makes sense.
To bring that latency back down to an acceptable threshold, you have to throw more hardware at the problem.
Just buy more servers.
But adding thousands of new machines increases the surface area for hardware failure,
Oh, right.
which in turn severely complicates your update rate and index freshness.
Because machines are constantly dying while you're trying to update them.
Exactly. Every parameter tweak creates a cascading ripple effect across the entire physical architecture.
To really ground this multiplier effect, we have to look at the historical metrics Dean shares, comparing Google's scale in 1999 to their scale in 2009.
The growth curve is almost difficult to conceptualize.
It's absurd. Over that single decade, the number of documents they indexed increased by roughly a factor of 1,000.
From tens of millions of pages to tens of billions.
Right. And over that exact same 10-year window, the queries processed per day also increased by roughly 1,000x.
So the sheer volumetric load on the system, the amount of data stored multiplied by the frequency it was accessed, was essentially 1,000,000 times larger.
1,000,000 times. Concurrently, they increased the per document metadata by about 3x to support more advanced ranking.
Despite bolting 1,000,000 times more weight onto the chassis, the average query latency actually dropped.
This is the part that blows my mind. In 1999, users waited just under 1 second for a search result.
Which fell fast back then.
Right. But by 2009, that latency was driven down to under 0.2 seconds.
That is a 5x improvement in delivery speed while carrying an exponentially heavier algorithmic load.
But the craziest metric, the one that really shows the architectural leap, is the update latency.
Index freshness.
Yeah. In 1999, the architecture required this completely static batch process.
You'd submit a website, the crawler would find it, but it might take a month or two for that new page to actually be merged into the searchable index.
By 2009, they had driven that update latency down from months to minutes.
We are talking about an improvement factor of roughly 10,000.
10,000x. And you cannot solve a 10,000x bottleneck by simply buying faster hard drives from Seagate.
Physics literally won't allow it.
Right, which introduces the guiding philosophy of Dean's presentation. And honestly, it's a harsh reality check for any systems engineer.
The 10x rule.
The 10x rule. The architecture that perfectly solves your problem at your current scale will likely be the exact bottleneck that destroys your system at 10 times that scale.
You have to design your infrastructure with the assumption that it will be obsolete.
It's planned obsolescence, but for your own code.
Exactly. You build a system to handle a 10x increase in load, but you must actively plan to throw that entire code base away and build something entirely new before you hit 100x.
Google essentially performed invisible open-heart surgery on their architecture.
Over and over again.
Over that 10-year span, they went through 7 massive fundamental revisions of their core search system.
Swapping out the jet engines while the plane was flying.
Exactly. Ripping out the foundational storage layers, changing how indexes were partitioned,
Altering the communication protocols across their server farms.
all while actively processing billions of queries. And to you and me, the users, the homepage never changed.
It remained a clean white screen with a single search bar.
It's incredible. So to really appreciate the sophistication of that continuous surgery, we need to look at what the infrastructure looked like at the very beginning.
Oh, the slides from 1997 and 1999. They paint a picture of extreme hardware scarcity.
The physical reality of the google.stanford.edu era in 1997 is phenomenal.
Mismatched beige PC towers.
Stacked haphazardly on tables, bulky CRT monitors taking up half the desk.
They famously used Lego bricks to build the casing for some of their custom disk arrays.
Legos. Because buying standard industrial metal racks was too expensive?
And Legos allowed them to easily reconfigure the physical drive slots when they needed to swap out dead hardware.
It's so scrappy. Then moving into 1999, they transitioned to what is known as the corkboards era.
The slide shows rows of standard low-end PC motherboards.
They didn't even use server chassis. They just laid bare motherboards directly on top of literal sheets of corkboard.
Just to prevent the circuitry from shorting out against the metal racks.
It's the ultimate scrappy engineering environment. Wires are spilling everywhere. They are relying on consumer-grade storage drives.
In incredibly low-end network switches.
But on top of this fragile, literal fire hazard of a hardware layer, they had to design a robust distributed architecture.
Which brings us to the foundational debate of 1997, data partitioning.
Okay, let's unpack this. When you have too much data for one machine, you have to split it up. You have to shard it.
Right. And in any distributed database, how you define that shard key determines the performance profile of your entire cluster.
For an inverted index, which is what a search engine uses,
Which is essentially a dictionary mapping every word to a list of document IDs that contain that word.
right, you have two logical choices for how to shard it.
You can shard by word, or you can shard by document.
Let's walk through that. If you shard by word, you partition the dictionary itself across your servers.
So server A becomes the ultimate authority on the word dog.
It holds the document IDs for every single web page on the internet that mentions dogs.
And server B is the authority for the word cat.
Sharding by word makes single-word queries incredibly efficient. If a user searches just for dog, the load balancer sends that query to exactly one machine.
Server A reads its local disk, scores the documents, and returns the result. Very fast,
But the problem arises when you introduce multi-word queries.
which is most queries.
Right. If I search for dogs and cats, the system has to query server A and server B.
But it can't just return both lists independently. It has to find the intersection,
It needs to find documents that exist on both lists
calculate the proximity of the words to each other.
and generate a combined relevance score.
And doing that requires shipping massive amounts of postings list data across the network switch.
Which means server A has to send gigabytes of document IDs over the wire to server B.
Or they both have to stream their data to a central aggregator node.
And in 1997, utilizing standard 10 or 100 megabit Ethernet switches.
That volume of internal network traffic would instantly saturate the backplane. The network becomes your ultimate bottleneck.
It just chokes, which leads to the alternative, sharding by document.
What's fascinating here is why they chose this route. Under this architecture, the dictionary is replicated, but the document space is divided.
So server A holds a complete independent index for documents 1 through 1 million.
And server B holds the exact same dictionary structure, but only for documents 1 million to 2 million.
If we think about it like a massive physical library, sharding by word is like alphabetizing the entire library by author. You want Asimov, go to the A wing.
But sharding by document is like giving each librarian a dedicated wing of random books to search completely.
Exactly. So if we connect this to the bigger picture of their hardware constraints, document sharding elegantly bypasses the network bottleneck.
Because when a user searches for dogs and cats, the load balancer broadcasts that exact same query to every single shard in the cluster simultaneously.
Server A looks only at its own million documents, finds the best matches, and scores them locally.
Server B does the exact same thing for its slice of the web.
Then each server just sends a tiny packet back over the network.
Maybe just its top 10 document IDs and their scores.
The central aggregator simply takes those top 10 lists from each shard, merges them into a final master top 10, and serves the user.
The network traffic is virtually non-existent.
It's brilliant.
Furthermore, because all the metadata for a specific document lives on the same physical disk as the index for that document.
You never have to do remote procedure calls over the network to fetch PageRank scores or anchor text during the ranking phase.
Right. But document sharding introduces a massive physical penalty on the back end.
Because you don't know which shard contains the best answer.
Every single query must be broadcast to every single machine.
If I search for a highly obscure word like platypus,
You are forcing 1,000 physical hard drives to spin up their actuator arms,
execute a disk seek, and scan their local index.
even though 999 of those disks won't have a single document containing that word.
You wake everybody up just to ask a question.
That is the trade-off. You are trading network bandwidth, which was scarce and rigidly capped by their cheap switches.
For disk I/O and CPU cycles across the entire cluster.
Given the 1997 hardware reality, accepting the disk seek penalty to keep the network free was the superior architectural choice.
It perfectly illustrates how software architecture is totally subservient to the physical constraints of the hardware it runs on.
Always.
And speaking of hardware constraints, the presentation describes the crawling and indexing process of 1998 and 1999.
No, it sounds like absolute operational torture.
It really does. It was a monolithic batch process. They didn't have sophisticated distributed task queues.
No, they relied on basic Unix command line tools.
They would spool up a massive crawl, extract the links, write everything to raw disk files.
And then execute a multi-day indexing run.
And there is zero checkpointing.
That's the part that hurts my soul.
If a machine panicked and crashed on day 3 of a 4-day indexing run,
They didn't have a save state to resume from.
the data was corrupted, and they had to clear the disks and start the entire batch process over from the beginning.
Keep in mind the physical environment here. These were bare motherboards sitting on cork.
Heat distribution was terrible, components failed continuously.
But the most terrifying engineering challenge Jeff Dean highlights from this era is a concept he calls programming with adversarial memory.
Here's where it gets really interesting. In modern cloud computing environments, we operate under the assumption that RAM is perfect.
When you write a variable to memory, you trust implicitly that it will remain exactly as you wrote it.
But these early PC-class motherboards were incredibly cheap. They lacked ECC, error-correcting code memory.
They didn't even have basic parity checks enabled.
And a parity bit is essentially a primitive hardware checksum.
Right. If a stray cosmic ray or a minor voltage fluctuation causes a physical bit in the RAM to flip from a 0 to a 1.
ECC memory will detect the anomaly and correct it on the fly.
But without ECC, that bit flip happens silently. The hardware actively corrupts your data.
And the operating system has no idea it happened.
Dean shares a legendary anecdote about this exact problem.
The sorting disaster.
Yes, they were running a massive sort operation on 1 terabyte of data.
And sorting is a highly memory-intensive task. You're constantly reading chunks of data into RAM, comparing them, and writing them back out.
Because the hardware was silently flipping bits during these comparisons, the final output of the multi-day run wasn't perfectly sorted.
It was only mostly sorted.
Mostly sorted.
Yeah.
Certain blocks of data were entirely out of order because the CPU had evaluated a corrupted memory address.
And just made the wrong sorting decision.
Blaming your own code for days before realizing the physical silicon is straight up lying to you.
That is a uniquely painful engineering experience. We've definitely been there in one form or another, but at this scale.
And if you reran the exact same terabyte sort on the exact same hardware,
The output would be mostly sorted in a completely different way.
because the bit flips were purely stochastic physical events.
Experiencing that level of hardware betrayal forces a complete paradigm shift in how you write software.
You have to abandon the pursuit of perfect, specialized hardware.
You accept that hardware is fundamentally unreliable and will actively sabotage your system.
Therefore, you must build resilience, checksums, and redundant verification directly into the software application layer.
You assume failure is the default state?
That philosophy of software-defined reliability became the bedrock of their next major phase.
Because by 1999, the web was expanding exponentially. User traffic was skyrocketing.
And the disk-seek penalty of their document-sharded architecture was hitting a hard physical limit.
Every query waking up every spinning disk was no longer sustainable.
They needed to bypass the physical disks entirely for the bulk of their traffic.
Which led to the 1999 architectural revision, the introduction of a dedicated cache server layer.
In distributed systems, a cache sits in front of the primary data store. It serves as a high-speed, short-term memory bank for the most frequently accessed data.
Dean notes that they cached two specific things: the index results, which is the actual list of document IDs that match a query,
And the document snippets, which is the short block of contextual text you see beneath the blue link on the search results page.
By placing these cache servers between the load balancers and the back-end index shards, the impact on performance was staggering.
They've regularly achieved hit rates between 30% and 60%.
That metric is wild when you think about the scale.
It means for every 100 searches coming into Google, up to 60 of them never even touch the core index shards.
The cache server intercepted the query for weather in London, realized it already had the pre-computed results in its local RAM from an identical search a few seconds ago.
And instantly returned the page.
A single rack of cache machines could suddenly absorb the workload of thousands of back-end index servers.
It drastically drove down average query latency.
Ironically, the most common queries, the ones with the most ubiquitous words, are mathematically the most expensive queries for an inverted index to process.
Because the postings lists are so massive. Caching those specific heavy queries provided a massive reduction in systemic load.
However, introducing a stateful caching layer into a distributed system creates a terrifying new vulnerability.
You have effectively built a dam holding back a massive reservoir of user traffic.
And whenever the core index was updated, that dam had to be broken, the danger of the cache flush.
The cache is only useful if the data is accurate.
Right.
When Google executed an update to their main index shards, bringing in new websites or updating PageRank scores, the existing data sitting in the cache servers was immediately invalidated.
To ensure users didn't receive stale results, they had to flush the cache completely.
The moment you run that flush command, your hit rate goes from 60% instantly down to 0%.
Every single query coming from the internet, including those massive heavy queries for common terms.
Suddenly bypasses the empty cache and slams directly into the back-end index shards at the exact same millisecond.
It creates a classic thundering herd problem.
The presentation explicitly describes this as a period of severe latency spikes and systemic capacity drops.
The back-end infrastructure has to absorb the full, raw, unfiltered force of the global internet.
While the cache servers slowly warm back up and begin storing the new popular queries again.
It's a brutal transition state. Everyone listening has probably experienced a modern app suddenly lagging right after a major update pushes. It's that exact same principle.
Exactly. But caching only masked the underlying speed issue. It didn't solve the fundamental read bottleneck on the disks.
To squeeze more performance out of the back-end shards for the 40% of queries that didn't hit the cache, they had to attack the physical size of the index itself.
If we connect this to the bigger picture, the size of the data on disk dictates how long the physical actuator arm of the hard drive has to read.
In the 1997 architecture, they used a simple byte-aligned format for the index.
A document ID was assigned a rigid 32-bit slot. The position of the word within that document was given a 16-bit slot.
From a CPU perspective, byte-aligned data is incredibly clean and efficient.
Processors are built to read data in fixed chunks, like 32 bits or 64 bits.
The software parser can just jump linearly through the memory addresses without having to do any complex boundary calculations.
But the drawback of fixed-width, byte-aligned formats is that they are terribly inefficient regarding physical storage space.
Right. If a document ID is just the number 5, you are still forcing the disk to store 32 bits of mostly leading zeros.
When you have billions of document IDs, those wasted bits compound into gigabytes of bloated data.
Reading those gigabytes requires the physical hard drive platter to spin longer, tying up disk bandwidth.
And the processor ends up sitting idle. It's starved for data, waiting for the mechanical disk to finish reading.
Okay, let's unpack this. So what does this all mean for the architecture?
They realized that CPU cycles were scaling much faster than physical disk speeds.
They could afford to make the processor work substantially harder if it meant they could shrink the physical footprint of the data on the disk.
They traded compute sweat to save I/O time.
The counterintuitive solution was migrating the entire index to complex, bit-level encodings.
Instead of fixed 32-bit slots, they utilized aggressive mathematical compression algorithms.
Jeff Dean explicitly lists several of these in the presentation: inner encoding, gamma encoding, Rice-Kate encoding, and varint blocks.
Let's dig into the mechanics of these because it really highlights the brilliant minutia of systems engineering.
Take unary encoding, for instance.
Instead of representing the number 5 in binary within a fixed 32-bit block.
Unary encoding simply writes 5 ones followed by a 0 as a terminator.
So the number 5 takes exactly 6 bits of physical space instead of 32.
And algorithms like gamma and Rice-Kate are significantly more sophisticated.
They're designed specifically to compress sequences of integers where the numbers tend to be small.
In a search index, you rarely store the absolute document ID over and over. You stored the delta.
The difference between the previous document ID and the current one.
Because these lists are sorted, the deltas are usually very small numbers.
Rice-Kate encoding uses quotients and remainders based on the power of 2 to pack these small deltas into a microscopically small number of bits.
They also heavily utilized varints, or variable length integers.
In a varint, the most significant bit of each byte acts as a flag.
If the flag is a 1, it tells the CPU parser, hey, this integer isn't finished yet, keep reading the next byte.
If the flag is a 0, the parser knows the integer has ended.
It allows you to store the number 5 in just 1 byte, while still allowing the flexibility to store the number 5 billion across 5 bytes when necessary.
By rewriting the storage layer to use these aggressive bit-level compressions, they shrunk the total physical size of the massive index by roughly 30%.
30% is huge. But the trade-off is that the CPU can no longer just blindly read the data stream.
It has to meticulously evaluate every single bit, look for terminator flags, calculate Rice quotients.
And reconstruct the original integers on the fly. The parsing complexity skyrocketed.
But the physics equation heavily favored that complexity.
Because modern CPUs execute instructions in fractions of a nanosecond.
Hard drives execute physical seeks in milliseconds. A CPU is orders of magnitude faster than a mechanical disk.
By spending a few extra CPU cycles to decode the complex bit stream, they reduced the physical amount of data pulled off the disk by 30%.
The net result was a massive speed-up in query processing times. The CPU easily outpaced the mechanical latency it saved.
It's a gorgeous engineering compromise. Embrace software complexity to fundamentally sidestep a hardware physics bottleneck.
But as user growth continued to explode into 2001, even highly compressed disks weren't fast enough to serve the back-end load.
Which brings us to a phase shift in distributed architecture, the accidental supercomputer.
As the sheer volume of daily queries continued to double, Google had to scale out their back-end to maintain their latency targets.
Remember the document sharding model? Every query wakes up every shard.
The only way to increase your queries per second capacity in that model is to create exact replicas of your shards.
If shard 1 holds the first million documents, you can't just have one machine serving it.
You build 10 identical physical machines, all holding an exact copy of shard 1's data, and you put them behind a load balancer.
When a query comes in, the load balancer sends it to whichever shard 1 replica is currently least busy.
To handle the planetary scale of their traffic, they had to add thousands upon thousands of these replica machines across their data centers.
But every single one of those cheap commodity servers came with a small amount of built-in RAM, random access memory.
Here's where it gets really interesting. If you zoom out and look at the cluster as a single organism,
And you sum up the total RAM across all those tens of thousands of replica machines,
the aggregate memory pool became astronomically large.
they crossed a critical threshold where the collective RAM across the entire server farm was finally large enough to hold an entire uncompressed copy of the World Wide Web's search index.
They didn't need to read from the spinning hard drives anymore for the core serving path.
They initiated the in-memory revolution.
They pulled the entire inverted index off the platters and loaded it directly into the lightning-fast RAM across the distributed cluster.
The physical disk seek penalty was completely eradicated from the critical path of a search query.
The architectural shift from disk-based retrieval to RAM-based retrieval fundamentally altered their performance metrics.
The positives were immediate. Raw system throughput exploded.
And they saw a dramatic, systemic decrease in what engineers call tail latency.
Let's unpack tail latency, because it is the ultimate metric of a healthy distributed system.
Your average latency might look great, say 50 milliseconds, but average latency hides the outliers.
Tail latency looks at the 99th or the 99.9th percentile of your queries. It's the worst case scenario.
If your 99th percentile latency is 3 seconds, it means 1 out of every 100 users is having a miserable, broken experience.
And at Google's scale, 1% of users is millions of people.
The presentation provides a highly specific example of a query that generated severe tail latency in the disk-based era. The phrase, circle of life.
The mechanics of that query are brutal.
Circle of and life are 3 of the most ubiquitous words in the English vocabulary.
The inverted index postings lists for those 3 words contain millions upon millions of document ADs.
In the old disk-based architecture, resolving that query required the system to read gigabytes of compressed data off the physical platters just to execute the intersection logic.
To find documents containing all 3 words in proximity, it choked the disk bandwidth and took an agonizing amount of time.
But once those massive postings lists were resident in RAM, reading gigabytes of data took almost no time at all.
RAM throughput operates in gigabytes per second without any mechanical seek penalty.
Those painful worst-case tail queries were suddenly executing in milliseconds.
It sounds like an absolute engineering triumph.
It was. But moving the entire index into RAM across tens of thousands of machines introduced an entirely new class of systemic instability.
So what does this all mean?
This raises an important question about distributed variance.
Right, because when a single user query is fanned out and touches 1,000 different machines simultaneously,
The final search result page cannot be rendered until the absolute slowest machine out of that 1,000 finishes its math and returns its data.
You are bound by the performance of your slowest node.
And in a massive cluster of cheap commodity hardware, the probability of variance is incredibly high.
Dean points out that a machine might be slow for 100 different reasons.
It could be experiencing a minor network packet loss.
Or a hardware memory controller might be overheating.
Or, incredibly commonly, a basic Unix background process. A cron job spins up to compress system logs or rotate files.
That cron job steals 20% of the CPU cycles on that one specific machine for just 2 seconds.
But because every single search query requires an answer from every single shard,
that one machine running a background log rotation suddenly causes the entire global search engine to lag for every user hitting the cluster during that 2-second window.
the variance of a single node becomes the variance of the entire system.
A rogue maintenance script holding up the knowledge retrieval of the entire planet. Classic move.
To mitigate this, they had to build incredibly complex timeout mechanisms and redundant request routing.
Like, if shard 1A is slow to respond, immediately fire the same request to shard 1B and race them to see who finishes first.
Right. But variance wasn't the final boss of the in-memory era. The ultimate threat to a distributive system this wide is the query of death.
The query of death.
It is an inescapable reality in systems that utilize massive parallel fan-out.
When your architecture broadcasts a single user's text string to 10,000 backend servers simultaneously, a perfectly malformed string can trigger a catastrophic failure.
We're talking of an edge case bug in the C++ parsing logic.
Maybe the user types a highly specific combination of bizarre Unicode punctuation marks.
That causes the text parser to enter an infinite loop.
Or triggers a buffer overflow that causes the application to panic and crash.
If that query was sent to a single machine, one machine would crash, the load balancer would route around it, and the system would survive.
But in this architecture, the load balancer broadcasts that poison pill to thousands of backend servers at the exact same millisecond.
It's an accidental digital superweapon.
The query hits the cluster, triggers the parsing bug simultaneously across the fleet, and instantly terminates thousands of backend processes at once.
A significant percentage of the global capacity simply vanishes into thin air.
To survive that reality, they couldn't just write perfect code.
Perfect code doesn't exist.
No. They had to build immune systems.
They implemented canary requests. Before broadcasting a complex query to the entire fleet, they would send it to just one isolated machine.
If that machine instantly died, the system recognized the string as a poison pill, quarantined the query, and returned a safe, degraded error page to the user without taking down the wider network.
It's software mimicking biology, building a system that learns, isolates threats, and heals itself.
And that culture of continuous adaptation leads us directly into segment 5, which covers the overarching theme of Jeff Dean's career.
The experimentation engine.
If you distill the 2009 presentation down to a single philosophical takeaway, it is this. The most important feature of a massive information retrieval system is not its speed nor its raw capacity.
It is the ease and velocity with which engineers can experiment on it.
Dean states it plainly. Faster turnaround on experiments equals more experiments run.
More experiments run equals a statistically higher chance of discovering better ranking algorithms.
Which yields a better search engine.
But you cannot run complex mathematical experiments on a billion web pages using basic command line tools.
You need foundational infrastructure dedicated to data manipulation.
This specific need drove Google to invent 3 custom infrastructure pillars that essentially birthed the modern era of big data and distributed computing.
Dean briefly outlines them, but their impact on the industry cannot be overstated. First is GFS, the Google File System.
Before GFS, engineers had to think about data in terms of specific physical hard drives.
If a data set was too big for one drive, you had to manually write code to split it across 2 drives and track where everything lived.
GFS abstracted all of that physical complexity away.
It allowed the engineering teams to treat tens of thousands of disparate disks across thousands of individual machines as one single, massive, universally accessible hard drive.
GFS inherently understood that commodity disks fail constantly.
When a file was written to GFS, the system automatically broke it into smaller chunks and replicated those chunks across at least 3 different physical machines.
If a motherboard caught fire and a drive melted, the GFS master node simply detected the missing chunks, seamlessly copied them from the surviving replicas to new hardware.
And the engineers never even received an alert. It provided unbreakable storage at a planetary scale.
But massive storage is useless if you can't process the data.
That led to the second pillar, MapReduce.
To write a distributed program that runs across thousands of machines, you usually need a deep understanding of network socket programming, distributed locking, and fault tolerance.
MapReduce democratized supercomputing for the internal teams.
MapReduce separated the logic of the data processing from the execution of it.
An engineer just had to write a simple map function, say, extracting the text from a web page, and a reduce function, counting how many times the word dog appeared.
The MapReduce framework automatically handled everything else.
It distributed the code to the machines holding the GFS chunks, executed the parallel processing, handled the massive network shuffling of the intermediate data.
And if a machine failed halfway through the job, MapReduce automatically reassigned that specific task to a healthy node.
It allowed a junior engineer with a new idea for a ranking signal to process petabytes of data across 5,000 machines with just a few dozen lines of C++ code.
The velocity of experimentation skyrocketed.
But the third pillar is perhaps the most critical for solving that 10,000x improvement in update latency we talked about earlier.
The invention of Bigtable.
Bigtable was designed to be a highly scalable, semi-structured storage system.
While GFS was great for storing massive, immutable files, Bigtable was built for online, highly efficient, low-latency access to deeply structured per-document information.
Remember the monolithic batch process of 1999? If you wanted to update the PageRank score for a document, you have to lock the entire massive database, rewrite the data, and rebuild the index, which took weeks.
Bigtable utilized advanced data structures, specifically log-structured merge trees, to fundamentally change how data was written.
If we connect this to the bigger picture, Bigtable turned random, chaotic database updates into sequential writes.
It allowed thousands of different distributed processes to update per-document metadata asynchronously at the exact same time without ever locking the underlying database tables.
That asynchronous, lock-free architecture was the absolute magic key.
It allowed the live serving system to continuously ingest rapid-fire updates from the web crawlers while simultaneously serving thousands of read queries per second to live users.
It is what brought index freshness from months down to a matter of minutes.
With GFS, MapReduce, and Bigtable in place, the life cycle of a search experiment became a highly tuned pipeline.
When a search quality engineer devises a new mathematical model for ranking documents, they start completely offline.
They use MapReduce to read petabytes of historical index data out of GFS, apply their new algorithm, and generate a massive parallel prototype of what the new search results would look like.
At this offline stage, CPU efficiency and query latency don't matter. They are purely evaluating the qualitative output.
They take the new prototype results and run them through human evaluation systems.
Actual human raters compare the old search results side by side with the experimental results to determine if the new algorithm actually surfaces more relevant information.
If the human raters validate the model, the experiment graduates to live traffic.
They push the new algorithm to a small, isolated cluster and route a tiny fraction, maybe 0.1% of live random user queries to the experimental system.
They watch the A/B test metrics like a hawk. Do users click the top result faster? Do they hit the back button less often?
But this rapid rollout of complex experimental models creates a profound organizational friction within the company.
You have two distinct engineering cultures operating with directly opposing mandates.
The search quality teams are incentivized to deploy these massive, mathematically heavy new algorithms because they demonstrably improve the intelligence and relevance of the search results.
But on the other side of the floor, you have the infrastructure and site reliability teams.
Their entire charter, their entire bonus structure is tied to keeping query latency under 0.2 seconds and ensuring the site never, ever crashes.
A new heavy algorithm that requires twice as many CPU cycles to execute is their literal worst nightmare.
Dean emphasizes in the presentation that managing the human element, maintaining constructive, respectful friction between quality innovators and the stability guardians, is just as crucial to the success of the system as the MapReduce code itself.
They had to build automated profiling tools that allow the infrastructure team to instantly prove to the quality team exactly how much their new model was degrading systemic performance, forcing them to optimize the math before full deployment.
It's a continuous, negotiated compromise between intelligence and speed.
And as Dean wraps up this keynote, he turns his attention away from the battles they had already won and looks toward the unsolved frontiers.
Segment 6 covers the architectural challenges of the future. And what is so striking is that more than a decade later, the computer science industry is still actively wrestling with the exact bottlenecks he identified.
His first major frontier focuses on cross-language information retrieval.
The conceptual goal is beautiful. Dismantle language barriers entirely.
If a user in Japan searches for a highly specific medical treatment, and the best document on the planet regarding that treatment is written in Spanish,
The system should find the Spanish document, translate it flawlessly, and serve it to the Japanese user in milliseconds.
the concept is beautiful, but the mathematics are terrifying.
If you attempt to translate every single document in your index into the 50 most common languages, you have just magnified the physical size of your storage layer by a factor of 50.
But the real bottleneck is the computational complexity of the translation models themselves.
Dean provides a deeply humbling statistic in the source material.
In 2009, utilizing their state-of-the-art statistical machine translation systems, translating just one single sentence required the infrastructure to execute roughly 1 million discrete lookups in a multi-terabyte distributed language model.
1 million operations for a single sentence. Now multiply that latency by the billions of sentences indexed across the internet.
You are no longer just doing fast inverted index keyword matching.
You are forcing the CPUs to calculate probability distributions across vast matrices of linguistic data in real time.
The infrastructure required to serve deep learning language models at scale was and remains an astronomical engineering challenge.
The second massive frontier he outlines is one that every corporate IT department on Earth understands: the nightmare of access control lists, or ACLs.
This is the fundamental challenge of building a unified search architecture that respects privacy and security boundaries dynamically.
Think about the drastically different security profiles of the data you interact with daily. You have private emails in your inbox that absolutely no one else on the planet should ever be able to query.
You have a shared project document that exactly 12 specific coworkers have permission to read.
You have a broad corporate wiki page available to all 100,000 employees of company.
And then you have public internet pages available to billions of anonymous users.
This raises an important question regarding architectural design. How do you engineer a single, unified retrieval system that can efficiently apply those wildly different security constraints at query time without degrading performance?
The optimal engineering solution for a highly restricted 12-person document is completely antithetical to the optimal solution for a public web page.
For the restricted document, you might do early binding. You physically embed the 12 permitted user IDs directly into the search index next to the document data, so the system can filter the results at the lowest possible disk level.
For a public web page, doing any kind of permission check is a massive waste of CPU cycles.
And the complexity compounds exponentially because human sharing patterns change dynamically.
A document might be restricted to 5 people on Tuesday, shared with a 1,000-person mailing list on Wednesday, and published to the open web on Friday.
The search index has to instantly update its internal security posture to reflect those changes, because serving a private document to an unauthorized user is a catastrophic failure.
Dean points out that maintaining entirely separate siloed search architectures, one highly secure system for emails, and a completely different fast-updating system for the public web requires far too much engineering overhead to maintain.
The holy grail of IR infrastructure is building a single, highly parameterizable engine that can automatically construct an efficient custom retrieval path on the fly, based entirely on the specific security constraints of the query being executed.
Finally, he touches on the ultimate algorithmic frontier: the chaotic, unstructured nature of human data.
The internet is not a cleanly formatted relational database.
Data with clear, neat, semantic labeling represents a microscopically small fraction of human knowledge.
The rest of the world is a noisy, semi-structured mess. Information is trapped inside badly formatted HTML tables, scanned PDF documents, deeply nested web forms, and inconsistent text blocks.
The challenge of the future is not just retrieving documents that contain keywords, but building systems capable of actually understanding the semantic relationships within that chaotic data.
Pulling structured entities like extracting the exact price, location, and date of an event from a deeply messy paragraph of text, and combining that extracted knowledge with redundant data from other messy sources to establish objective facts.
It is an endless algorithmic frontier that pushes the boundaries of artificial intelligence.
Okay, let's step back and look at the grand synthesis of this journey. In the span of a single decade, from 1997 to 2009, we watched an architecture evolve from literal Lego bricks and corkboards into a distributed, in-memory planetary supercomputer.
And the most striking realization is that they did not achieve this scale by simply waiting for Intel and Seagate to manufacture faster hardware.
They achieved it by constantly questioning their own foundational assumptions.
They accepted hardware failure not as a rare anomaly to be avoided, but as a fundamental rule of nature to be engineered around.
They ruthlessly and continually balanced the unforgiving trade-offs between CPU cycles, disk I/O bandwidth, internal network capacity, and mathematical complexity.
So to wrap this up, let's look at the key takeaways. Number one, the 10x rule. The architecture that got you here will break when you scale by an order of magnitude. Plan for obsolescence.
Number 2, hardware will lie to you. Assume failure at the physical layer and build resilience into your software.
Number 3, experimentation velocity is your ultimate competitive advantage. Build the tools that allow your team to test new ideas quickly and safely.
And number 4, embrace complex software to bypass physical hardware bottlenecks like they did with bit-level compression.
If there is a core takeaway from Jeff Dean's philosophy that applies to anyone building complex systems, whether that's a software application, a massive logistics network, or a corporate organization, it is the acceptance of planned obsolescence.
You cannot be afraid to take a sledgehammer to your own beautiful architecture. You have to constantly build the machine that builds the machine.
To close out this deep dive, consider a final provocative thought.
The next time you sit down at your laptop, pull up a search engine, type a mundane query like how long to boil a soft egg, and receive a flawless list of results in exactly 0.12 seconds.
Take a moment to look past the clean white interface.
Think about the ghost of that 1999 server farm. Think about the adversarial memory, the cosmic rays causing silent bit flips in the dark.
Think about the incredible mathematical density of the bit-level compression algorithms saving physical disk space, and the thousands of discrete machines coordinating their responses in mere milliseconds to dodge a query of death.
Realize that the invisible, magical digital infrastructure supporting our modern society isn't static.
It is a living, breathing entity designed with an inherent expiration date, quietly waiting to be entirely ripped out and rewritten from the ground up, just to keep pace with the endless scale of human curiosity.
Find your weirdest edge case and share it. We love this stuff. Tell us what to cover next. Leave a comment and rating. Subscribe if you enjoyed. Thanks for listening. Until next time.